Hello, and thank you for tuning in. Ancortek software-defined radars can be utilized for a number of industrial, scientific, and academic purposes. Today, we'd like to demonstrate some of these possibilities. Frequency-modulated continuous wave, or FMCW for short, can allow an operator to observe both the range and Doppler velocity of a moving target. In our first example, we've placed the radar approximately 4 meters off the ground and observed a pedestrian walking below. The figure on the right demonstrates the range and Doppler velocity observed, with color indicating the power amplitude of the return. Notice that the majority of the power received comes from the pedestrian's torso. This return can be used to immediately tell how fast the person is walking down the road. Furthermore, we can see the movement of their front and back feet, as one is moving forward while the other remains nearly stationary. In this scene, we've taken the raw output of the radar and created a short movie clip of the range Doppler map over time. You can observe that as our pedestrian switches from her left foot to her right, she will pause and the observed side loads decay. As she proceeds to move forward, the return from her forward-moving leg is caught by the radar and is displayed as a faster object than her torso. Further analysis of these returns would shed evidence on whether the person was walking or running, as well as their gait and posture. Ancortek's software-defined radars can be used to perceive many other objects as well, as we demonstrate using a four-door sedan. In this scene, we plot the range Doppler map generated from an FMCW signal inside Ancortek's imaging GUI. Even without the aid of a camera, we can clearly observe the vehicle approaching the radar, as evident from the polarity of the Doppler shift and the reducing range. Taking an academic perspective, Ancortek's software-defined radar can be used for exhibiting many known works against real-world scenarios. In this example, we demonstrate how the observation angle between the radar and target affects the perceived Doppler velocity. Here, even though the vehicle maintains a steady relative forward velocity, the radar will perceive the velocity as changing due to the change in angle between the radar and the target over time. Next up, we're using the FMCW range display from our GUI to perform a simple ranging experiment. Here, we've mounted the radar onto a moving cart and roll it towards the side of a building. The GUI will lock onto the target with the largest power return, and we can track our distance in meter from the building as we approach closer and closer. Ancortek's software-defined radars are applicable for both outdoor and indoor operation. Here, we've set up the SDR RF980 module in a small office environment to track a person's motion using the GUI's range waterfall display. The waterfall display is an excellent tool for tracking changes over time. We can observe that as the person walks closer towards the radar, the range reading approaches 0. Then, as she walks away, the range increases to the right. The color of the display indicates the power amplitude of the return signal. There's no range compensation being performed, so the signal will become weaker as she moves farther and farther away. In this experiment, we're moving back outdoors and switching gears to velocity measurements as we've set up the radar to track the motion of an oncoming vehicle. We've configured the GUI to run a velocity scope display and set up the radar waveform to a simple continuous wave. Now, we can easily detect and track the oncoming car and measure its relative velocity. Beyond making direct measurements, Ancortek software-defined radars can be used for inverse SAR imaging, as demonstrated in this example. Here, we've taken several measurements of a moving car as it drives past the radar. Those collections were then exported into MATLAB and processed to create the ISAR image you see on the left. Our 2.4 and 5.8 GHz line of equipment possesses excellent through-wall performance properties. In this demonstration, we've set up the radar in FMCW mode with a range velocity map in view. The radar has been positioned directly against the drywall segment of the office, and we can clearly track an individual's movements as they enter the room, sit down, and then depart. Special attention should be made when recreating this experiment, as different walls will respond differently depending on the material they are made from and which frequencies you're using to transmit and receive. Our final demonstration is on the topic of micro-Doppler analysis. Specifically, We've set up the radar to analyze the forward motion of a person as they are walking, and compared this response to a person running. By exporting all of our collections from the GUI into MATLAB, we can build a graphic of the Doppler frequency shift over time of these two situations. Besides the runner taking a second getting up to speed, you can clearly observe the greater frequency shifts of the runner's legs as they advance and recede quicker than the person walking. You can also observe that the runner is changing the position of their forward and receding legs quicker than the person walking. By applying different machine learning algorithms to these profiles, we could characterize different walking motions and patterns for an automated classification system. You can find further documentation, informational videos, demonstrations, and much more at www.ancortek.com. Thank you for watching.